With this question, a sound wave has wavelength of 0.34 meters, a frequency of 1 kilohertz, and we want to find speed, and we are told that the answer we end up with should be 340 meters per second. So there's the shopping list. Given wavelength, given frequency, wanting speed. But did you notice the prefix in the frequency number? So we swapped kilo with times 10 to the power 3. There's the formula. Numbers go in, and we remember units. With this question, a beam of light is traveling 384,400 kilometers to the moon from Earth, and we want to calculate the time it takes. We don't seem to have been given much information in the question, but we can look up the speed of light on the data sheet. So there's the shopping list. We have speed from the data sheet, we have distance from the question, but we also have to deal with the kilo prefix in that distance value, and we're trying to find time. There's the formula. Numbers go in. If we're then stuck with how to do the maths, draw a triangle. That's what the blue star is trying to show. Cover up the T, and that tells you that the next line is the distance number divided by the speed number. So we do that, get the answer, and remember units. Well done, you smashed those calculations. Now we're looking at what happens when light goes into another material. So the practical point of this is that it's how lenses work, and literally anything to do with images has lenses in. Like your phone camera, your eye, telescopes, microscopes, binoculars, projectors, car headlights, and so on. Any device like any of these works because of this stuff. The one thing you have to understand, which makes everything else make sense, is that when light enters a new material, it changes speed. This is just like if you go for a run, but then move on to a different surface. You will change speed too. You might start off running on a road, then go onto grass. You might then go onto a beach, and then down into the water, maybe then on into some muddy area. Every time you move into a different material, your speed will change. The picture here is trying to show that when a light beam is hitting a slower material, like glass, at an angle, then there's a corner that will hit that slow material first. Can you see it? That corner will now be moving really slowly, but the other corner, still in air, will still be going rapid. So there's a turning effect. I tried to show that in pink. Can you see it? The picture below is of the same thing, just zooming out a bit. This is how rays of light are normally drawn. Not the great fat things like in the diagram at the top. The final picture is introducing you to some very important angles. We draw a dotted line at the point where the ray meets the new material. This dotted line is at 90 degrees to the new surface. This dotted line is called the normal line. Normal is just a maths word meaning that something is at 90 degrees to something else. Anyway, the angle between the normal line and the incoming ray is called the angle of incidence. Incidence is just a fancy name for incoming. When the light ray has gone into the new material, the angle between the normal and that ray continuing on is called the angle of refraction. This whole thing of light changing speed as it enters a new material is called refraction. So the refracted ray is the ray once it is in the new material. And the angle between the dotted normal line and the refracted ray is called the angle of refraction. If the ray of light is going into a slower material, like glass or water, can you see that the ray turns towards the dotted normal line? I'm trying to show that in pink. But if the ray of light is going into a faster material, from a slower material, the ray of light will turn away from the normal. And again, we can label the angles of incidence and refraction. Here's a ray diagram where both things are happening. Light going into a slower material, and then escaping back into a faster material. Can you see that as the light enters the slower material, the ray bends towards the normal, and as the light enters the faster material again, the ray bends away from the normal? And of course, the angles of incidence and refraction are there too. The incidence angles are in green and the refraction angles are in blue. As I said, the main use of this is in lenses. A lens makes a small, upside-down image of the world in front of it, at the point where the rays come together. And the reason the lens does this to the rays is refraction. Notice that the rays going through the middle of the lens, so that would be straight along the dotted normal line. If you were to draw one in, don't change direction. They just go straight through. People find labeling the angle of incidence and refraction tricky. So here are a few more examples. Again, green is incidence and blue is refraction. As you see each one, think about whether that makes sense to you. In each case, the angles are from the dotted normal line. That's the whole reason we draw on the dotted normal line. Here, the light ray is going into a slower material, so it bends towards the normal. Here, the light ray is going into a faster material, so it bends away from the normal. Here, the light ray is going into a slower material, so it bends towards the normal. Here, the light ray is going into a faster material, so it bends away from the normal. Don't let surfaces at jaunty angles throw you. It's all the same process, and all the same angles. Have you ever seen a harbor where boats are tied up? Hopefully you have, but have you ever thought about what the hell is the point of a harbor? Like, why not just tie the boats down on the shore? The idea of a harbor is that the crazy energy of waves from the sea is calmed right down, in the harbor. How does that happen? In part, it is because a lot of the sea waves crash against the harbor wall and bounce back into the ocean, like in the bottom picture. But even with the bottom picture, there has to be a large gap in the harbor wall for boats to come through, and sometimes the gap is much bigger, like in the top picture. So what about all the energy in water waves still coming in? The answer is that water waves, and all other waves, spread out as they go through a gap or spread round a corner. So that energy from the waves is spread out across all the water surface over the harbor. So rather than crashing waves, the water in the harbor gently rises up and down, as all that energy has been spread out. You're doing really well, and I know there has been a lot of information. Just 2 final details about this wave spreading out to do, and then a final worked example. Bring it. So firstly, this spreading out of a wave as it goes through a gap or around a corner or object or obstacle is called diffraction. And secondly, longer wavelength waves diffract or spread out much more than shorter wavelength waves. In these pictures you can see the diffraction angle, the spreading angle, is wider for the longer wavelength waves than for the shorter wavelength waves, which have not as wide a spreading angle. The same is the case with waves spreading around the side of an obstacle. The spreading angle for long wavelength waves is much wider, so the energy is more spread out right across the area. Why do we care? One example of how this would affect you is if you go for a hike in the hills of Scotland, you'll find that your mobile phone doesn't work. That's because the mobile phone signal is carried by microwave light, which has a fairly short wavelength. So it doesn't spread out round hills at all well. Your signal will be very patchy at best. So get out in those hills, but take a map, because diffraction physics means you won't be able to rely on your phone for signal for Google Maps. Finally, let us smash a last worked example. Then it is home for tea and medals. Here is a diagram of a wave. Based on the diagram, calculate the wavelength of the waves. If you count the number of waves, there are 4 of them. I've drawn them in different colors here, to try and make it really clear, but be aware that in the exam it will just be black. You count 4 waves then, and we know that 4 waves take up a length of 20 meters. This is kinda basic numeracy really, not a formula, but it does then make sense that the length of just one wave is going to be 20 meters divided by 4. This comes out as 5 meters, the length of one wave, and this is what the wavelength is. Part B. If these are water waves, and a person in an inflatable ring rises up and down once every 4 seconds, calculate the frequency of these waves. So, what the question is telling you, without telling you that it is telling you, is the time period of the waves. Time period, remember, being the time that one wave takes to happen. So capital T is 4 seconds. Way after frequency, so F is question mark. As usual then, copy out the formula from the formula sheet and use your shopping list to put the numbers in. If you're then stuck on how to carry on, draw the triangle and cover up what you're trying to find, in this case, F. This tells you how to finish off the calculation and get the final answer of 0.25. But don't forget the units, which in this case are hertz. Finally, given your answers to parts A and B, calculate the speed of the waves. Well, from part A we have the wavelength, from part B we have the frequency, and now, from part C, we are looking for the speed. So now we've done the shopping list. Pick a likely looking formula, put the numbers in, do the maths, then remember your units. That's the waves topic. Well done.